Now that you have a pretty good understanding of the Ethernet protocol, we're going to turn our attention to the only other really layer 2 protocol we're going to talk about, and that's the address resolution protocol, or ARP. Now, there's a little bit of discussion out there as to whether ARP is really a layer 2 protocol or a layer 3 protocol. It kind of serves as both. Some people would call it a layer 2.5 protocol. Again, the OSI model is just kind of a reference that allows us to kind of talk intelligently about protocols and the services they provide. So for the most part, I don't want to argue the semantics too much. For this purpose, I'm going to call it a layer 2 protocol. It doesn't really matter too much as long as you understand the service it provides as a protocol. Now, with that in mind, think about the fact that computers don't generally know MAC addresses of other systems right off the bat. And think about that. When let's say you ping another system, you've probably used ping before. What do you type in? Well, you generally type in an IP address, not a MAC address, right? So if you want to ping 4.2.2.1, you type in ping space 4.2.2.1. However, the network layer is important, right? And even though we haven't talked about it specifically, you probably already know that. Systems use IP addresses to find and communicate with other systems, and you also have to use an IP address if you want to communicate with something outside your network because you need services provided at the network layer like routing. So we generally do things with IP addresses, but MAC addresses are important because that's how switches within a network get things to the right place. And even if you're leaving your current network and going to another one, you have to go through your router, which has a MAC address, which your switch has to know about. So here's the important question based upon that. If computer A only has the IP address of computer B, and if a MAC address of the remote system is required to communicate, how does computer A find computer B's MAC address? That's information we have to have, but we don't have it. Well, fortunately, that's where ARP comes in. ARP is used to map MAC addresses to IP addresses. So it's used to make that connection. So I know the IP address of a system. I need to know its MAC address so communication can move forward. And that's what ARP is going to allow us to do. And that's why it's called the address resolution protocol. It helps us resolve one address to another. Now, this process occurs through a pretty simple broadcast and reply sequence, and we'll go through that in detail here in just a moment. But there is this process of sending an ARP broadcast out to the local network segment and receiving a reply from the person who has the address and information that you need. Now, keep in mind, ARP is not routable outside the local network. It's only meant to be used to find MAC addresses, and MAC addresses are at the data link layer, right? They're not routable. They're not going out to other networks. They may only go out to your router. If you're talking to something, if I'm talking to 4.2.2.1 and that's on another network, I'm concerned about the MAC address of my router so I can communicate to that router and pass that traffic along using network layer features, using things like IPv4 or IPv6, which we'll talk about in the next section. Now, I mentioned broadcast traffic already, and it's important to note that ARP does use broadcast, and that's important because it means you'll see ARP traffic in most packet captures you create yourself. So if just on your local machine you fire up a packet sniffer right now, you fire up Wireshark and leave it on long enough, you'll probably see some ARP traffic because ARP caches don't last forever. They expire, and things will send ARP broadcasts to attempt to find specific devices. And since it's a broadcast, you'll see those broadcasts for anything that's occurring on the same network segment. If you'll remember, we talked about broadcast quite a bit earlier in the introductory material in the course. So all important things to note. But with that said, let's dig in a little further and start looking at the structure of the ARP packet. So you're looking at an ARP header now, and it's not too much more complicated than the Ethernet header we just looked at. It does have a few additional fields, but nothing too overwhelmingly complicated. So I want to go through those pretty quickly here. The first field we'll see is a 2-byte hardware type field, and that's used to specify the protocol type being used at the data link layer. So in this case, there would be a code associated with that, and most of the times you'll see Ethernet as the hardware type, which is just going to be the number 1. It's going to be code 1. Protocol type specifies the internetwork protocol the ARP request is intended for. So for most cases, that's going to be IPv4. I didn't mention this earlier, but ARP is generally used for hardware to network address translation in conjunction with IPv4. IPv6 actually uses a different neighbor discovery mechanism, which we'll cover a little bit later. But ARP generally going to be seen in use with IPv4 based communication. After that, we have the hardware length field, which is the length of the hardware address. And so, of course, we mentioned hardware type, and based upon that type, we have a hardware address length, which in this case, we're talking about Ethernet, and we've talked about MAC addresses already, which are 6-byte addresses. So the value here would tell us that we have 6-byte addresses, and that would provide information that's usable for the rest of the protocol and let us know if any of the existing hardware addresses that are noted have to be padded or anything like that. Following that, we have the protocol length field, which is just 1 byte, and it's the length of the addresses used in the upper layer protocol. And when I say upper layer, in this case, I mean IPv4, so the one immediately up above in the network layer. After that, we have the operation field, which is a 2-byte field. And this is really just going to tell us whether the packet is an ARP request or an ARP reply. The value of 1 would be a request. The value of 2 would be a reply. And that's generally the most we're going to see out of the ARP that we're looking at in this course. So very straightforward, very easy to figure out what's going on there. Now, after that, we have a lot of fields that are very similar. So we see sender hardware address, which is a 6-byte field. We see sender protocol address, and a 4-byte field, target hardware address, which is 6 bytes, and target protocol address, which is 4 bytes. And what we're really looking at there are basically just MAC addresses and IP addresses. They might be named a little oddly, but consider that ARP can be used with other things, right? So we have to specify the hardware type, which is Ethernet, the hardware address length, protocol type and protocol address length, and those kind of define what the values of these remaining fields are. So we see sender hardware address, that's 6 bytes, conveniently enough. We know that MAC addresses are 6 bytes. We see the protocol address, which is 4 bytes, conveniently enough. We know that IP addresses are 4 bytes. So you kind of see what's going on here. And we have two groupings. We have sender hardware and protocol addresses and target hardware and protocol addresses. And what that means is going to be a little variable depending upon whether we're looking at an ARP request or reply. So rather than talk through that further, I'm actually going to show you an example through our examination of normal stimulus and response for the ARP protocol, and you'll start to see how these fields make sense in the context of an ARP request and an ARP reply. What you see on the screen now is the normal ARP request and response process. We're looking at normal ARP stimulus and response. And what we have here on the left, we have two sections. We have the request and the response separated out. And on the left, we have a single computer. And that computer wants to communicate with another system, but it doesn't have its MAC address. So to figure that out, we're going to utilize broadcast traffic to get the answer we need. So what's important to note is on the left, we have that individual system. Its source IP address is 192.168.0.101. Its source MAC address is F2, 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 F2 repeated, so 6 bytes of F2. And you see that listed there under source IP and source MAC of the first packet data. And in the middle here, we have a switch, and on the right, we have all the other computers of the network. So that's important to note that that is a switch there, not necessarily a router. So in this case, we see that this host, 192.168.0.101, knows the address of the system it wants to communicate with. In this case, we see that listed under target IP, which is 192.168.0.1. However, it does not know the MAC address, and we can see that because target MAC is all zeros. All zeros is not a valid MAC address, so that's the piece of information that's missing. And anytime you're looking at ARP request, you can see the piece of information that's missing by looking at this target MAC field or looking for all the zeros. And I'll show what this looks like in Wireshark here in a second. But in this case, what we have is the machine on the left is simply asking a question. It says, who has 192.168.0.1? And when I say that, it's saying, whoever has that, please tell me what your MAC address is. Now, in this case, since it doesn't know the MAC address, it can't communicate with the host. So if it can't communicate with the host, how does it get a response from it? Well, the answer is in how it sends the communication. In this case, it sends it as a broadcast packet to every device on the local network segment within that broadcast domain. And you see that reflected on the image here. It sends that packet out, and the packet goes to every single host on the domain. So in this case, there are 3 of them. It goes to all 3 of them. It relies on broadcast traffic, which again is different from unicast, which is from one host to another host. This is broadcast to everyone on that broadcast domain. Not routable, so it won't go outside the network, but it stays inside the network. Now, in this case, since it's going to every machine on the network, we can see what happens with the response down at the bottom of the screen here. In this case, only one machine has the IP address 192.168.0.1, and it's the only one that responds to this ARP request. So it takes the source IP and puts its own IP there, and then it gives its MAC address. In this case, its MAC address is 02F202F202F2. You see that in the source MAC area under the ARP response below. Its target IP and target MAC is the same source IP and source MAC from the request. It's just flipped. So it's basically just responding to that broadcast and sending that information back. It's answering the question, who has 192.168.0.1, and it's answering it by saying 192.168.0.1 is at 02F2, 02F2, 02F2. So it's basically responding with the MAC address that was previously unknown. At this point, communication can actually begin because the system on the left, 192.168.0.101, now has all the information it needs to construct a proper packet, construct the Ethernet header with the target MAC address. That's all available. So this is a pretty straightforward process. Very simple. Only really 4 main fields that we're concerned about here. I mean, we talked about a few other fields, how to identify a request versus a reply. But in terms of actually movable and trackable data, these are really the 4 fields we're concerned about, and they're pretty straightforward. So let's look at an example of ARP resolution as it would appear in the actual packet itself. So that's what we have on the screen here. And this is from a file called arpresolution.pcap.ng. So you can actually look at this file yourself, open it up from the course materials, and play around with it. Now, this is not the exact same example mentioned in the diagram that we just looked at. It's a little bit different, but that's okay because I want you to look at a little bit of a different example. Same process, just different addresses being used. Now, in this case, we have a couple numbers here on the screen, and we'll use those to kind of navigate around. First of all, you can see the Ethernet header is present here, and you can see very easily we have a source address, so a source MAC address, which is identified by the number 2 there, and then the destination is broadcast, right? And I mentioned that before. We send an ARP request to the broadcast address, which is all Fs in this case, so it's all Fs in every octet. And that will send the packet to every system on the broadcast domain. So everybody's going to receive this because it's destined to the broadcast address. So we see that there. Note as well, like under the 2, you see type ARP in the Ethernet request. So we talked about ether type, and one of those is ARP, which is 0806. Now, if you look at the ARP resolution protocol area, so the ARP header here, we see a lot of the fields we talked about, right? Like we see the hardware type is Ethernet, we see the protocol type is IPv4, which is expected, hardware size and protocol size, 6 bytes and 4 bytes, representing MAC address and IP address, and the code in this case it's called the opcode, is request. So we know this is indeed an ARP request. From there, we have the addressing information, and this is very similar to the example we just looked at. We have a sender MAC and IP address, which those are known. In this case, our sender is 192.168.0.114, and it looks down, and you can see we have a piece of missing information. It does not know the MAC address for the IP address 192.168.0.104. That IP address is mentioned in number 4 there, and we see all zeros in number 5, which indicates that we don't know this MAC address. So in this case, what we're doing, if we had to verbalize this, is the host 192.168.0.114 is sending a broadcast out and saying, hey, what is the MAC address of 192.168.0.1? Please, whoever you are, respond with that information, right? And so that's the ARP request process as outlined in an actual packet. Really lines up well with the example we just looked at. So with that said, let's look at the response that pairs with it. Now here's the response, and this is just the second packet in this ARP resolution.pcap.ng packet. We see a lot of the same information, but in this case, note that the sender and target information is switched. First of all, we see the opcode is a reply, so we see that by the number 1 there. Now in this case, the sender IP address is the device we were concerned about. By number 3, it's 192.168.0.1, and we actually have the MAC address now. In this case, it's that 0013460B22BA MAC address, which we can see through resolution as a D-Link device, maybe the network router or something like that. What was the source is now the target. So basically we have the system, this D-Link device, is responding with this information and sending it to 192.168.0.114. It's replying with that information. Again, the request was sent out and everybody on the broadcast domain received it, but only the system that actually had the IP address being looked at responded with that information. right? So we're just flipping the source and destination around, or at least in this case, the original destination was broadcast, and now we actually have a proper unicast response. So we're not looking at broadcast, we're looking at a one-to-one communication sequence here. So pretty straightforward. Get around, play around with this. Definitely look at arpresolution.pcapng yourself. It's only 2 packets, very easy to follow. But also go ahead and on your system, start a packet capture. And like I said, since ARP is broadcast traffic, you'll see a lot of ARP requests. Now, you won't necessarily see replies because, again, those are not broadcast. But if you do see a reply, it's probably because it's related to your machine, either something it's requesting or something it's responding to. So play around with that, and very easy to pick up the concept that is normal stimulus and response for the ARP resolution process. Next, I want to talk about another type of normal stimulus and response for the ARP protocol. And in this case, we're going to talk about gratuitous ARP. And now when something's done gratuitously, that doesn't always, it's not always a good thing, but in this case, trust me, it is. So we talked about the ARP request and reply process and how we use that to map IP addresses to MAC addresses. And that's a pretty simple process, but if you think about it, if that had to be done every single time a system communicated with another system, that would be a lot of traffic, a lot of noise, and maybe not the most efficient thing. For that reason, systems maintain a cache of ARP entries, normally called an ARP table or an ARP cache. This is just a simple listing or mapping of IP addresses to MAC addresses that have been discovered by a system and maintained on that system. The idea is that there's a timeout on those, but they last for a certain amount of time and it can be referenced instead of having to generate a new ARP request every single time communication wants to happen. It's really an efficiency thing and it makes things a lot cleaner. Not necessarily maybe as required nowadays with modern fast networks, but especially back in older days when networks are much slower and you had to be really conscious of bandwidth usage. You didn't want ARP traffic flying around just constantly. So ARP tables made that a little bit easier. Now, there's a little bit of an issue here, though, when you consider what happens when a system IP address changes, right? So we have systems that exist in DHCP ranges, and maybe that IP address changes for some reason. In that case, all these other systems on the network that have an ARP table entry that map a specific IP address to a MAC address, they'll be invalid, right? That MAC address will now map to a different IP address and they won't be able to communicate. And there could be a little bit of a time gap in the time it takes for that cache entry to expire and a new request to be generated. And that could cause connectivity issues. So that's where gratuitous ARP comes in. A gratuitous ARP is called so because it doesn't, it's not necessarily solicited. So gratuitous ARP is really, the purpose of that is to kind of advertise a new IP address or MAC mapping to other devices on the network so they can update their ARP tables. In this case, as we have on the screen here, we'll say that the system on the left, which has, as we've listed, a source IP of 192.168.0.101, we'll say that it actually just got that IP address. Let's say it had a different address and it just got that one. So instead of having the connectivity problems I just mentioned, it's going to actually send out a special ARP request packet to the broadcast address. And that will force the other systems that receive it, which in this case will be all of them in the broadcast domain, to update their ARP cache with the new information. And now there are a couple special things here. Notice that the source IP and the target IP are the same, right? Because we're not actually looking for the MAC to IP mapping of a specific system. We're actually just advertising the one associated with our system, right? So this is how we identify a gratuitous ARP, is by having the same source IP and target IP. We'll have a source MAC, and of course the target MAC will be 0 in this case. And this is what a gratuitous ARP looks like. We can see a similar example of gratuitous ARP in the file arp_gratuitous.pcapng, and this really reflects a similar situation to what we just talked about. In this case, we'll see that the source is this Intel NIC here. It's identified by the number 1 there is 000347B7F2F5, and we're sending to the broadcast address, which is all Fs, so every device on the broadcast domain is going to get this packet. Now, if you look down at the ARP section and the section highlighted by the blue 2 there, we see our sender MAC and sender IP address. In this case, the sender IP address is 24.6.125.19. We see its MAC address there. And then the target IP address is the same as the sender address. So again, it's 24.6.125.19, and the target MAC address is all zeros. So this is what a gratuitous ARP looks like. It's still an ARP request, technically, although it's necessarily not requesting anything other than the recipient host to update their ARP tables. But you'll see that Wireshark detects this, and right above the 2 there, right above sender MAC address, it identifies this and says, is gratuitous true? true. And in this case, it will also identify gratuitous ARP packets in the packet list window under the info column. So you would see that there as well, which is reflected at the bottom right of this screen, right above the close button. You see it says info gratuitous ARP for 24.6.125.19. So this, again, looks like a normal ARP request. The only thing that identifies it specifically as a gratuitous ARP is the fact that the sender and target IP address are the same thing. So the idea being that when another system receives this, they will then update their ARP cache on that system to reflect the mapping of the sender IP address, that 24 address, to the 000347 MAC address. So that's the stimulus and that's the response. There's no packet that's going to come back. There's no response back because we're not requesting information. So the stimulus is this gratuitous ARP request packet, and the response is the change that happens on the recipient systems, whether it's a computer or a router or what have you. It's going to update its ARP cache table and prevent the connectivity issue we talked about earlier, where an IP address change might cause an issue. So again, you'll see this often when an IP address of a system changes. You'll also see it when a new network interface is installed into a system. You'll see that this process goes on to advertise the IP address, newly gathered IP address associated with the MAC address. So those are really the two most common situations where you'll see gratuitous ARP in play. Now I want to talk about abnormal stimulus and response. We've already talked a little bit about spoofing and how that can be done at the Ethernet layer, and that really has a serious implication in terms of ARP and how ARP cache poisoning can be done. If you remember, we talked about ARP cache poisoning earlier when we talked about tapping into the wires. It's a technique you can use to intercept packets between two machines, and that's a useful technique. Of course, it's also a technique an attacker can use to perform a man-in-the-middle attack, and it's quite easy to do. An attacker can do it just by virtue of being on the same local network as you are, and it's something that is not necessarily hard to defend against, but it's something that's cumbersome enough that most people don't do what is required, which is actually usually hard coding ARP tables or using some type of ARP watching software that will prevent this from occurring. But I do want to take you through this process. It's a little bit complex, but bear with me here. I want to show you what's going on. So in this case, we have three devices in play, and we're viewing this, at least in this diagram, from the victim's perspective, right? So we have a Cisco router, we have an HP attacker system, and we have a Dell victim, and they each have their own IP addresses or MAC addresses. In this case, I've not listed the IP address of the attacker because it's not really important, not necessarily to the scenario. But in this case, what the attacker wants to do is intercept communication between the victim and the router. So that's basically intercepting all of the victim's internet communication, everything going between that victim and upstream to another network out on the internet. So that's what we're doing here. We're going to do that via spoofing. And it's really a three-step process. First of all, the attacker sends an ARP request directly to the victim instead of broadcasting it. So you see there it has a destination MAC that is the same MAC address of the victim rather than the broadcast address. The attacker asks, who is at 172.16.0.107? Please tell 172.16.0.1. But wait a minute. 172.16.0.1 is the router IP address, and the MAC address that's actually provided along with this request is actually the attacker's. It's not the actual MAC address that actually matches the router. So is that allowed? Well, it is actually, and quite unfortunately, and that shows how ARP can be easily abused by spoofed information being inserted into these things. We're actually taking advantage of the caching feature and the ability to basically put anything we want into these ARP packets. In this case, the victim replies with this information, telling the attacker system that 172.16.0.107 is at the MAC address specified, identifying the victim, that 002170 MAC address there, and that completes that initial transaction. Now in step 2, the attacker sends an unsolicited ARP reply to the victim and says, hey, just so you know, 172.16.0.1 is at the 0025B3 MAC address, which is actually the MAC address of the attacker and not the MAC address of the router. The attacker here is tricking the victim into thinking that it is the router by taking advantage of the insecure nature of ARP, and it's doing this kind of both directions, right? So we're seeing this again from the victim's perspective. So you'd see this if you're capturing packets on the victim system. You'd see all these ARP requests and replies going on. So the victim now thinks that it is talking to the router, but it's actually talking to the attacker when this part's done. Now, this is victim's perspective. What you don't actually see is that simultaneously, the same process is happening between the attacker and the router. It's doing the same thing, but it's doing it with the router, and it's basically tricking the router into thinking that it is the victim system. So there's two layers of communication going on right here, and trickery on both sides. And essentially, it's tricked both devices into thinking it's the other device. So the router will now be communicating with the attacker when it thinks it's communicating with the victim, and the victim will now be communicating with the attacker when it thinks it's communicating with the router. So this effectively creates a man-in-the-middle situation, and at this point there would be software running on the attacker system that would route the communication effectively between these two devices, right? There's a little bit of trickery in the software realm that has to happen to route this traffic properly based upon what's going on. And of course, there would also generally be some type of sniffing software. Of course, Cane Enable is something we mentioned and we use, and it can certainly be used for a number of nefarious activities. Just sniffing packets alone might yield some interesting information. So there's definitely a few different things that can go on here, but this kind of demonstrates the process that's used to conduct ARP spoofing and really take advantage of the ARP process. Now, I have an example I want to go through this later. We're actually going to talk about man-in-the-middle much more later when we talk specifically about security. Here, I just want to demonstrate that ARP can be taken advantage of via spoofing and taking advantage of those ARP caches and trying to manipulate those, since ARP replies can be unsolicited, which is what is used here. I do want to show you here that we do actually have a packet capture that contains an example, and it's actually this example we just went through. So the exact diagram we just showed is the example that's demonstrated in the file arp-poison.pcapng. So here you can see by the number 1, we have the initial request with the spoofed MAC address. We have the reply at packet 55 number 2 there with the reply from the victim, and then number 3 there we see the unsolicited reply that's sent from attacker to victim, saying that the IP address 172.16.0.1 is actually at the attacker's MAC address. So you can see that process kind of play out there. We're not going to go as in depth on that now. Again, we'll talk about that really in depth. We'll go through every single packet in the security section of the course later on. But I did want to show you that if in case you do want to get around and play around with this a little bit, we do have the arp-poison.pcapng file that you can dig around in. So with that said, that's going to bring us to the end of our discussion on ARP. So again, ARP is a very important protocol. Communication wouldn't really exist without it, at least for IPv4. Again, IPv6 uses a different mechanism, but for IPv4 communication, we really rely on ARP to map our IP addresses to our MAC addresses so we can have communication both inside and outside the network. So we talked a little bit about stimulus and response for that. Stimulus and response for normal ARP is pretty straightforward. We have the request and reply process. We also have the gratuitous ARP process, which is really an efficiency gain when an IP address is changing or maybe a new network interface is inserted into a system. Beyond that, we do have the potential for abnormal stimulus and response with ARP cache poisoning coming into play, and that's something that really takes advantage of the fact that ARP is ultimately an insecure protocol, and the way most systems handle it's an insecure protocol. Now, generally, you can mitigate some of these risks by using endpoint detection tools that will detect this sort of thing going on, so that they'll keep a record of these ARP requests and look for the patterns that match the activity we talked about. Or some people choose to hard code ARP tables, especially on relatively static systems like in ICS networks or things like that. So there are mitigations that can be provided, but by default out of the box, ARP is vulnerable to being exploited in this way that allows for man-in-the-middle attacks. But again, nonetheless, ARP is a very important protocol. It's one you want to understand. Fortunately, it's very simple to do so. So understand the normal and abnormal stimulus and response here, and you're well on your way as we make our journey up the stack and start looking at other protocols.